Swayam Prabha. Digital India. Educated India.
Once again, welcome to MSB lecture series on advanced transfer chemistry. I am sure you are having wonderful time in reading chemistry. Let me begin the lecture with an introduction to transition elements. Before I start about the introduction and discussing more about transition elements, let me give the course outline, and of course I had already discussed history of periodic table. I am going to start soon introduction to transition elements and their general properties. Once that is done, I would begin with an introduction to coordination chemistry that includes electron neutrality principle, Capert model, Werner's coordination theory in detail, and then isomerism. Once that is completed, I shall begin with theories of metal ligand bonding that includes valence bond theory, crystal field theory and molecular orbital theory. I would give more attention to crystal field theory to explain all possible geometries and their splitting, and then I shall tell you about metal-metal multiple bonding including quadruple and quintuple bonding, and ligands are an important components of coordination chemistry. So, I shall do the classification of ligands by donor atoms. There are several ways to do the classification, but the most appropriate and the suitable method is to do the classification of ligands by donor atoms, and then that can tell you about different type of ligands including sigma donor and pi acceptor and the corresponding complexes, and preparation of important coordination and organometallic complexes also are included. And once that is done, I shall tell you more about Sidgwick rule and 18 electron rule and also effective atomic number, and later I shall discuss two important reactions as far as the application of organometallic compounds and coordination compounds in homogeneous catalysis is concerned, that is oxidative addition and reductive elimination reactions, and also their significance in homogeneous catalysis. Once it is done, if time permits, I shall tell you about synthesis and characterization of various ligands and organometallic reagents, and also I shall tell you about reactivity of transition metal complexes, and if time permits I shall briefly discuss about important symmetry and multinuclear NMR or interpretative NMR or interpretative molecular spectroscopy in order to help you in understanding and characterizing organometallic compounds and coordination compounds. And at the end or in between I shall tell you about the application of transition metal complexes in industry and medicine. With this course outline, let me start the introduction. Of course, the books I have referred in framing this course are given here. F.A. Cotton's 6th edition Advanced Inorganic Chemistry, and of course Huhi Inorganic Chemistry 4th edition, and another interesting and very important and informative book Inorganic Chemistry by C. Housecraft and A. G. Sharpie, and also I am using Inorganic Chemistry 4th edition by Shriver and Atkins. And this periodic table is very important for a chemist, and once we know the periodic trends and also the position of each element in the periodic table and how these properties are varying about the charge to size ratio and all those things, understanding chemistry of whether main group elements or transition elements would be very easy, and give more emphasis for at least remembering 30 elements in the periodic table and writing their electronic configuration. When we talk about these transition elements, or metallic elements, they have incomplete D or F shells, and if any metallic element that has an incomplete D or F shells are called as transition elements. So, they make up 55 of the 118 elements. That means we have 94 natural elements and 24 man-made elements, out of which 3D, 4D, 5D series we have 9 electrons each, that means 27, and we have 4F and 5F, we have about 28 elements. Together we have 55 elements that constitute transition elements. Although scandium and yttrium belong to the D block, their properties are similar to those of lanthanides. The chemistry of D block and F block elements differ considerably, and of course structural aspects would explain these properties in a very clear way. When we look into D block, as I mentioned, we have 3 blocks, 3D, 4D and 5D. Each group of D block metals consists of 3 members and is called a triad. For example, if I consider chromium, molybdenum and tungsten, or if I consider nickel, palladium, platinum, or copper, silver and gold, or cobalt, rhodium, iridium in this fashion. Okay. So, each set is called a triad. Metals of the second and third row are sometimes called the heavier D block elements, and if you see, the chemistry of 3D elements differ considerably from 4D and 5D series, whereas 4D and 5D have lot of resemblance and they have very similar, almost very similar properties. And here ruthenium, osmium, rhodium, iridium, palladium and platinum are collectively known as platinum group metals or platinum metals. When you see some book stating platinum metals, you should not confuse about only the platinum. The platinum metals refer to these 6 elements together, that is ruthenium, osmium, rhodium, iridium, palladium and platinum. So, properties of the D block transition metals vary not only within the triad as I had mentioned, but also in the left and right groups. The group 3 to 5 metals are referred to as early transition metals, and they are generally oxophilic and halophilic. That means those having electronic configuration of D1, D2 and D3, they have up to 5 electrons in their valence shell considering 2 s electrons. They are referred to as early transition elements, or almost having up to D5 electrons are considered as early transition metals. And once we cross manganese and go further towards the right side of the periodic table, they are considered as late transition metals. So, smaller number of D electrons in the early metals and the hardness of these elements explain their affinity towards hard donors such as oxygen and halogens. That is the reason they are called oxophilic and halophilic. And metallic radii of scandium to copper, that means varies significantly starting from 166 picometer to 128 picometer, and this is smaller than those of 4D series. For example, yttrium starts with 178 picometer to silver 144 picometer, and those of 5D series starts with lanthanum at 188 picometer to gold having 146 picometer. So, however, similarities between 4D and 5D can be seen due to the lanthanide contraction. I shall tell you more about lanthanide contraction later. And when you go down a group, the atomic radius increases markedly from the first to the second series as an additional electron shell is added. However, the atoms of the second and third elements tend to be very similar in size. Again, this is due to the lanthanide contraction which occurs across the F block. F block elements contract as an additional F electron is added across a period, and the core electrons are not really screening the outer valence electrons. So, this contradiction offsets the addition of an extra electron shell between series 2 and 3. So, this effect is most marked to the left of the D block just following the lanthanide contraction. So, after lanthanum of the scandium group and the atomic radii for zirconium and hafnium are almost identical, and these elements are very hard to distinguish. I shall show you the plot, then it becomes very clear. The effect has largely disappeared by the time we reach the copper group, and although silver and gold have almost identical atomic radii, their chemistries are quite different. So, cadmium and mercury have very different atomic radii and quite different behaviors as well. You can see the trends I had mentioned in atomic radii of transition elements. You can see the atomic radii is decreasing steadily until it hits manganese and iron, and then slowly this increases. And you know that as more and more electrons are added to the same shell, what happens? Effective nuclear charge increases. As a result, valence electrons are pulled more towards the nucleus, that resulting in the decrease of radii. But on the other hand, once it is half filled, we have the maximum. After that one, when you add more and more electrons to the d shell like d6, d7, d8, what happens? You have to consider inter-electronic repulsion also. Because of inter-electronic repulsion, what happens? The size increases. So, the trends are clearly seen, and the trends are very comparable among 3D, 4D and 5D series. So, the first period of transition metals behave quite differently from the second and third period. I had already mentioned the second and third elements in each transition group tend to behave very similarly to one another, since their atoms are of similar size, whereas the first period have distinct behavior. That means when you look into physical as well as chemical properties of 3D elements, they differ significantly compared to 4D and 5D series, whereas 4D and 5D have remarkable similarities between them. To understand the chemistry of the transition elements, one need to understand the effect that the d electrons have. Consider first the very different shapes of the d orbitals. When we have to understand the coordination chemistry and understanding of the shapes of various orbitals and their relative orientation are very important. I shall elaborate more when we go to the bonding concepts. Another interesting feature can be seen here. So, trends in standard enthalpies of atomization of transition elements is given here, and if you see here, yes, steadily as more and more electrons are added to the d orbital, enthalpy is increasing, and once it comes to a half filled electronic configuration, it dips and then rises again and falls considerably. That means enthalpy of atomization is steadily increasing and then it decreases. One should explain this one by looking into the electronic configuration and to what extent metal-metal bonding is playing a role. But the interesting thing is why it drops in case of manganese group having electronic configuration of Nd5NS2. That means it shows decrease in enthalpy of atomization. The reason is very simple. Here we have D5S2 electronic configuration, and when you have D5S2 electronic configuration, because they are half filled and they are stable and they are pulled towards nucleus more readily, and they have very minimum inter-electronic repulsion. As a result, electrons dislodging from their position is difficult. As a result, metallic bonding will be little weaker compared to others, and hence the enthalpy of atomization decreases here in this case. And if you are surprised to know what is atomization, it is almost like you can see pomegranate, picking one grain at a time and separating them is like enthalpy of atomization. Now they are all put together in the lattice. If you start taking out, that is very nicely comparable to the enthalpy of atomization. And this decrease in enthalpy of atomization for manganese group is also reflected in the melting point. So, let me show you here why Mn group shows decrease in melting point. That means, as I mentioned here, the enthalpy of atomization also drops. As a result, what happens? Taking out these atoms or separating these atoms will be very easy, and hence melting point also drops in these cases having Nd5NS2 electronic configuration. So, in the absence of bridging ligands, the formation of metal-metal bonds is difficult for these early transition elements. Okay, the reason is very simple. They do not have sufficient unutilized electrons in their d orbitals, and bridging ligands such as halides, amides, alkoxides and aryl oxides have available lone pairs that can be donated to the metal ions. Metal is in high valence state and empty orbitals are there, and coordination number is small. As a result, they have all ingredients to expand its coordination number and to accommodate more electrons in their empty orbital. As a result, what happens? If the ligands with sufficient lone pairs are available, they readily use them as bridging ligands. Organometallic compounds of these metals are known strongly to activate CH bonds in hydrocarbons. The reason is they are electron deficient compounds and they have vacant d orbitals. They readily undergo beta hydride elimination, due to which they are more reactive and thermally unstable. For example, if you take tetramethyl titanium, that is stable up to minus 40 degree centigrade, and then if you consider tetraethyl titanium, that is stable up to minus 60 degree centigrade. Above minus 60 degree centigrade, that readily decomposes because ethyl group has beta hydrogen. So, beta hydrogen elimination readily happens and that compound decomposes. That means if I ask a question about the stability of tetramethyl titanium and tetraethyl titanium, without any hesitation you can say tetramethyl titanium is more stable compared to tetraethyl titanium, because in case of methyl you do not have beta hydrogen, and however both are thermally unstable. Late transition metals are soft and have high affinity towards sulfur or selenium. That is the reason if you look into late transition elements including group 12, they exist in nature in the form of sulphide ores, for example cinnabar, PbS, zinc sulphide, etc. So, let us look into the common oxygen states of the first series of transition elements. You can see scandium group, the common oxygen state is +3. In case of titanium we have D2S2. So, group oxidation is +4, and also we come across +3 and +2, and they are little unstable. In case of vanadium we come across 2, 3 as well as 5 oxygen states, and in case of manganese we can see all possible oxygen states and up to 7, and in case of iron we will see 2 and 3 are the most common ones. In case of cobalt also +2 and +3 are more common. In case of nickel we see nickel 2 and in some cases nickel 4+, and copper shows +1 and +2 states, and zinc shows +2 oxygen state. Let us look into the nature of early transition elements. So, that has an implication on their properties. So, these elements are strongly electrophilic and oxophilic, and few redox reactions with an exception of titanium, and always less than 18 electrons will be there in their valence shell, and hence they can never obey 18 electron rule. I shall tell you more about why some elements can never obey 18 electron rule when I will be discussing in more detail this effective atomic number. And early transition elements are polar and very reactive. They have polar and very reactive MC bonds, whether it is alkyl or aryl, and few d electrons are there. As a result they are hard sigma donors, hard acids, and also they prefer hard sigma donors such as nitrogen, oxygen or fluorine, and they form weak complexation with pi acceptor ligands such as olefins and phosphines. Unless phosphines are strong sigma donor, early metals reluctantly form bonds with phosphines, and a typical catalytic process they promote is polymerization, and one should remember always, even with coordination number 6 and having octahedral geometry, they can never obey 18 electron rule. And just I have shown you d orbitals and their shapes here, and of course we have dz square, dxz, dyz and dx minus y square and dyz. Let us look into the ligands. Ligands are very important components of coordination compounds and organometallic compounds. Compounds of metal ions coordinated by ligands are referred to as metal complexes. So, that means in order to call a complex, it should have a metal ion or neutral metal coordinated by ligands, and most ligands are neutral or anionic substances. They can be ions or atoms or a group or a molecule, but cationic ones are also known, for example nitrosyl cation or tropylium cation. Neutral ligands such as ammonia, carbon monoxide are independently stable molecules in their free states, whereas anionic ligands such as chloride or cyclopentadienide are stabilized only when they are coordinated to central metals. So, I am going to show you the representative ligands. Okay. Common ligands are those with complicated chemical formula or long names are expressed in abbreviated forms. If we have to use routinely ligands having very lengthy name, then probably it is ideal to abbreviate and use the abbreviation, but somewhere in the beginning we have to give the expansion and detail about that ligand. So, those ligands with one donor atom are called monodentate ligands, and those with more than one donor atom are referred to as bidentate, tridentate, tetradentate or polydentate ligands. For example, bi, tri, tetra, etc. If both the donor atoms are bonded to the same metal, such ligands are called chelate ligands. The number of atoms bonded to a central metal is the coordination number, that is secondary valency. Okay. So, I have listed here the types of ligands. Of course, negative ligands or anion ligands are shown here, fluoride, chloride, bromide, iodide, oxide, nitrato, sulfato, amido, imido and hydrido, and here I have displayed neutral ligands. This is triphenyl phosphine and pyridine, acetonitrile, hydrazine, amine, ammonia is also called as amine, water called as aqua, carbonyl, CS thiocarbonyl. Again CS does not have an independent existence, but it can be generated in situ and can be used similar to carbon monoxide, and nitrosyl and ethylamine. Apart from these, we also have several other ligands like oxalato, bidentate ligand, or it can be one tetradentate ligand because of other two C double bond O oxygen atoms, and glycinato and ethylene diamine, bipyridine. Again bipyridine we have 2,2 bipyridine, 4,4 bipyridine, and this is bis diphenyl phosphonomethane, and this is 1,2 bis diphenyl phosphinoethane. The correct name should be 1,2 bis diphenyl phosphinoethane, because 1,1 bis diphenyl phosphinoethane is also there, and 1,2 diaminopropane. And when we look into tridentate ligands, we have diethylene triamine, or we also have terpyridine, and also we have a hexadentate ligand called EDTA, ethylene diamine tetraacetic acid. So, this is a symmetric bidentate ligand, ethylene diamine, whereas this one having an amino and carboxylato group is unsymmetrical bidentate ligand, and these are all ambidentate ligands where we have two different type of donor atoms are there, and they can also exhibit linkage isomerism. And when we look into macrocyclic ligands, they are the important macrocyclic nitrogen macrocyclic ligands, a chlorine ring, corine ring, porphyrin ring and crown ethers. So, valence shell electrons, in particular d electron configuration, controls the structure and spectral and magnetic properties as well as the reactivity of complexes. That means knowing the valence shell electronic configuration of d elements is very important. The theory of electronic structure is very important to understand the properties and reactivity and also their application in various aspects. The nature of the metal ligand bond can be understood by analyzing the molecular orbital diagram. Molecular orbital diagram can give clear picture of relative energies due to the interaction between the metal atomic orbitals and ligand orbitals. Bonding, non-bonding and antibonding molecular orbitals assist in understanding the properties and reactivity of metal complexes. Again I will be spending considerable amount of time in explaining the bonding concepts and also giving more emphasis for crystal field theory and molecular orbital theory to make you familiar with these bonding concepts, so that speculating their properties and reactivity would be much simpler. And materials made of transition metals show metallic properties. They are hard, malleable, ductile and good conductors of heat and electricity with high melting and boiling points. The utility of transition metals range from simple substances and alloys to electrical and electronic devices. Of course, this explains malleability of metals. Let me stop at this juncture and focus more about physical properties and other important properties related to transition elements in my next class. Until then, have a good time. Thank you.